Hello students, welcome back. This lesson is about tangency problems. We're going to look at it in three different perspectives, and first two of them are reviews. First, the simplest of all, graphs. When we have a graph of a function y equals to f of x at specified x value x equals to x0, this is the formula for the tangent line. Y equals to x prime of x0, that's the slope. And then from slope point equation we get x0 and then y0 as f of x0. We can break it down into step-by-step process like this. First find out y value, next the derivative, next the slope by plugging the x value, and then finally we get the slope point equation of the line by putting everything together. Well, let's go to one example, just one example. There are many, but they're all reviews, so let's do it as quickly as possible. Let's take this problem for instance. Okay, x naught is equal to 1, so what is y naught? Just this function evaluated at x equals to 1. So plug in 1 here, plug in 1 here. So what do you get? Square root of 1 is 1, so we get just 2. E to the 1 pi is 1, so we have 2e. What does that tell me? Y equals m x minus x0 plus y0 is the slope point equation, and then y naught we just calculated is 2e, and x0 was given as 1. Finally, if we find out what m is, then we are through. So let's find out m, the slope. What's the derivative? We have to use the product rule, I guess. So this is equivalent to x to the 1/2 power. So let's go ahead and use power rule and product rule. So we get 2 times 1/2, so x to the negative 1/2 power, and exponential stay the same, plus 2x to the 1/2 power stay the same, and the derivative of exponential function stay the same. So this is the derivative. Now let's find out the slope. And from here, plug in x equals 1. And that's 1. And then let's complete this computation. 1 to whatever power is just 1, so we get 1 and e to the first power. And then this is just 1, so 2e, so we have 3e. So m is 3e. So that's the quantity that'll replace m here. And what do we have? We have the solution, the slope point equation. Well, here's the solution. Oh, I don't have solution here. So this is a full solution. And then here's a verification through mathematical computation. And here it is. The function, the curve, and then the tangent line. And the tangent line looks like this. 3e x minus 1 plus 2. A little bit change of order, but everybody can see that this expression here is the same as that expression down here. So this completes a brief review on the tangency problem for the graphs. Next, implicit curve. We have to find out the derivative through implicit differentiation, and then we have to plug in numbers. Y prime is going to be my slope, and that's going to be my m value when evaluated. So we have the slope point equation like that. x0, y0, those are given usually. And in an exceptional case, when m is undefined, we're going to have a vertical line, v equals to x0. Let's see. What problem do we have? Okay, this problem looks complicated enough, and I don't think we did it in the implicit differentiation video problem set, so maybe it's a good time to do it here. Okay, alright. Let's anticipate my solution. Y equals m, x minus 1 plus 1 is going to be my solution if my slope is well defined. Or it could be the vertical line, and in this case slope is undefined, and in this case we're going to get the vertical line. But this is going to be exceptional case. Most of the time it's going to be like this. Okay, let's find out the derivative through implicit differentiation. Here we go. Exponential function, left hand side, stay the same, and we have to multiply the derivative of the inside. What's the derivative of the inside? X over y. So let's see, it's 1 times y to the negative second power. Excuse me, let's do it like that. I don't like to use quotient rule, so let me rewrite this into this form so that I can get away with quotient rule. Equals to 2x minus y squared. Okay, let's start from here and let's take the derivative implicitly. X y to the negative first power minus 1 stay the same, and let's take the derivative of the inside. Derivative of the first function 1 and y to the negative first power plus x times the derivative of y to the negative first power. And then don't forget y prime. Derivative of minus 1, that's 0, so I don't really need it. Plus 0. Or if you prefer, you can write plus 0 here. Now let's go over to the next. Derivative of 2x is 2. Derivative of y squared is 2y, and then y prime. Let's align this equality. Now, maybe a bit of a color coding as well. This is important quantity, so let's highlight in red. And again, this is important quantity. Okay, this is the implicit differentiation. Now we don't have to do any kind of algebra here. Plug in numbers. X equals to 1, y equals to 1. That's what we are doing. X is 1 and y equals to 1. So plug in x equals to 1 and then y equals to 1. And then minus 1, what do we get? 1 times 1 minus 1, this whole thing becomes 0, isn't it? Yeah, this whole thing will become 0. Next, how about this one? Times 1 to the negative first power. So this whole thing will become 1. X equals to 1, so this is 1. And then this one is going to be 1 times negative second power, so that's going to be 1 as well. Let's see, minus, let's export it over here, and then we don't have this anymore. So this whole thing is 1. How about this? Y is equal to 1, so no, times 1, so let's just remove that. A little bit further simplification, alright. This whole thing is 1 times 1 to the negative first power, so that's 1, minus 1, this whole thing is 0. In other words, this exponential part, e to the 0 power, is just 1. How about this part? This is 1. And then this whole thing is, again, just 1. And we have an equation like this. Shall I simplify just a little bit further? It is, without parenthesis, 1 minus y prime equals to, oops, 2 minus 2y prime. We're almost there. Let's get all the y prime terms to the left hand side, and then we're going to be through. Alright, move this 2y prime to the other side. We're going to get positive y prime over here. And then 2, flip this 1 to the other side. 2 minus 1, we're going to get 1. So that's what we're going to get. Y prime is equal to 1. So the slope is 1. We're going to get this. Y equals to 1, x minus 1 plus 1, or y equals to x minus 1 plus 1. So y equals to x. Let's see if this is right. Visualization. Yes, indeed, y equals to x. This line goes through this point, 1 comma 1. So that was a convincing evidence, and here is the full solution. Also, you can just open up the solution and then go through, well, a little bit of an abbreviated process here. By the way, I use quotient rule here. I usually don't like to use quotient rule because it's complicated, but looks like I did it over here. Anyway, we get the same solution, and we verify through Mathematicus visualization. Now the third example is parametric curves. We're going to talk about a bit of theory now and some further examples in the next video. Here's the theory. Parametric curves are given by a pair of two functions. Here's an example. X as a function of t, y as a function of t. And both are linear functions, and consequently we get something really simple. As a matter of fact, we have a line. Don't pay too much attention to this vector notation. And we're going to talk about vectors a bit later. This purple is the visualization of this particular curve. It's a line. Next, an ellipse. X is a function of t, x0 plus a cosine of t. Y is also a function of t, y0 plus b sine of t. And consequently, we have a curve, and it turns out to be an ellipse. As a matter of fact, I think we can visualize this thing. You see, as time changes, the position of x t and y of t moves around, and that position is tip of this arrow. We have sine and cosine, both are periodic, and that's why we have closed curve. See, the trace of moving particle, x of t comma y of t, turns out to be the curve. And that's how the parametric curve arises actually. Here's another example. We have x as a function of t, y as a function of t, and t changes, and we are going to get a point moving around. X is a horizontal position, y is vertical position, and the trace is the curve. We have a nice curve here, very beautiful looking curve aesthetically speaking, and this is the visualization. Oh, let's slow down a little bit. The point is x of t comma y of t, and the position of that is represented by the tip of this arrow, as a matter of fact, as a vector quantity. And x of t represents the horizontal position of this red dot, and then y of t is the vertical position. Both x and y are defined in terms of periodic functions, and that's why we have closed curve. One more example of parametric curve, and then we'll just end this video, and we're going to do the rest in the next segment. This one, another aesthetically beautiful picture. Looks like a butterfly. And let's slow down a little bit so that I can see the motion a bit better. And please pay attention to this red dot. And this is x of t comma y of t. X is horizontal position, y is vertical position. And then the arrow actually represents the direction, direction of the position vector. And if you're viewing it from the origin, you don't have to pay too much attention to that. The dot represents the parametric curve x of t, y of t, and the trace of it is a curve. So much for parametric curves. In the next video, we are going to talk about the calculus of parametric curves, especially in terms of tangency problem.